Now, you are on my website, but I haven't told you where to go yet, so just have it there for yourself, okay? All right, so check yourself, please. I need to see 1 through 8 on your desk now. If I don't see it, it's not there. Check yourself on the board now. If you're not logging out the computer anymore, it doesn't matter. 1 through 8 on your desk. This is 1 through 8. That's not concept. This is like yesterday's practice that I asked of you at the end of the day.
Stupid sick. I got 1 point left. And then number 7, I got 5.4. That's all I got. That's all I got. Yeah, I dropped to a
Mr. Chemistry, where you guys come on? Did you ever call you?
Yeah. That's 7.
I'm on a mission. Let me get through my mission. Okay, guys, so at this point, let's go ahead and check some of these together. I've heard 2 claims that you need help on 7, which is the one I knew you would need help on. What other? 6 and 7. Any more? 3, 4. Potentially 3, 4, 6, 7. Potentially. Let's see where we are here, okay? And it's something in foods. It's fine. It's just not good foods. Okay, so let's start with number 3. I will get you started. My expectation is that you can get started like by writing down the given, setting up your little train tracks. That's not difficult, right? Can you agree? So even if you're like, I don't know what the heck I'm doing about the stoichiometry process, you can still get me started. So if you're just like, meh, I didn't do it, shame on you for not even getting started, because that is minimum, okay? So for these, each of these, the givens are kind of loud and proud right here. You do not need to really be on the computer right now, so work with me, okay? If you're like the boss on this, then you just keep on listening to re-emphasize some of those points. What's carbon tetrachloride? CCl4, good. If you're going for molecules, okay, think about your mole map, right? Where are we at on the mole map? Hold your hand where you are. Hold your hand where we are, guys. Let's go. Particles, right? Particles, they only have a connection where? No. Particles is molecules, a form of a particle, and where do those go? Where do they go? Particles only have one connection. To mole. No, particles, let's review this again. We have particles which come in 3 flavors. What are they? Atoms, molecules, and formulations. Why do we have all these different things? Ionic, covalent, and elements, right? They're just different stuff in the world. We call them slightly differently. Then we connect that down here to what? Mole, which is always a 1. And then we connect mole to what? Well, using molar mass, we're going to get to mass. Where would we get that number? T2E. What number goes up here? Avogadro's, okay. And what's down here? Volume, and what number connects that? 22. Alright, so literally you cannot put anything but these numbers, right? This is 24 liters, by the way. And here we go. So I have molecule. Where am I at on my map?
Top.
On top, right here. I have to go where?
Mole.
Moles using what number?
6.02.
And that describes the number of what?
Or the molecules in the
Particles or molecules for this specific example. 6.02 times 10 to the 23rd molecules of CCl4 is equal to 1 mole of CCl4. I guarantee you, if you got this wrong, it's a miscalculation because you didn't put parentheses here and parentheses here when you divide it. That's generally a mistake people make. So once I'm in mole, I'm going to go to grams. Is there a connection for mole and mass? Yes. What is this? What is this guy's molar mass?
154.
154. Where do I put that? At the top. 154 grams is the molar mass of CCl4, and that's equivalent to 1 mole of CCl4. You guys can do your math there. On 5, I almost guarantee the problem was calcium nitrate's formula. So what is calcium nitrate's formula, everybody? Ca.
NO3.
NO3. 2, parentheses 2, right? So that's the piece that would be skewing, making the molar mass incorrect. So I would guarantee you, I would think that you would need to go back and check that, and that would fix your mistake. Let me scooch down to 5. No, was it 5 or 6? 6, thank you. So starting off with 4.54 grams of CO2, where are we on our mole map? Hold your hand there. So it's kind of like on the side, okay? If I want to go to liters, I'm going to go from here to here. Can I go from mass to liters? Not directly, right? So what's my indirect way? Mass to mole, mole to liter, right, or volume. So CO2 is carbon dioxide. I hear a prefix, that's how I know it's covalent, therefore I'm allowed to just plug the number in where I see dye. What number goes down here? Can somebody other than Bennett here? There's 30 of you, let's go. So grams of CO2 get on here. What's that number? 44-ish, okay. That's equivalent to what? 1 mole of CO2. Perfect. So grams of CO2 cancel. Now we're in moles of CO2, so I've made it here. And now I want to get to liters. What's the only number we can use for that? 22.4. Where does that go? On top, because that is the that's the number for liter. And 1 mole on bottom of CO2 cancels out moles. Get to liters. And now 7 is the one I actually want to go through slowly with you, okay? So hydrogen peroxide, what is that formula? H2O2, right? Hydrogen peroxide is something you've probably got in your storage cabinet at home. It's something we maybe even talked about in class, just as an example of how you can have multiple ratios. All right, so we have to start with this 1.160 moles of hydrogen peroxide. There's probably 2 ways to solve this problem, 3 ways to solve this problem. I'm going to go with what you tell me first, and then I'll make connections. So literally, you can go anywhere from mole, right? But here's the problem. You're going from mole of hydrogen peroxide to grams of oxygen, not hydrogen peroxide. So where do you guys want to go? But I can't go there because that's hydrogen peroxide, and that would take me straight to oxygen. That's apples and oranges, and I can't convert that. Say again? So you can't go from moles to grams because that would leave you stuck here. Then where would one go? Back to mole, which that's not helpful because we're going back to where we started. Moles of particles would give us a more viable method, because if we go to particles, which of these particles would we be going to? For this guy. Why is that a molecule? Because it's a covalent compound, right? So we would go to molecules. So then once we're in molecules, what could we dig into the molecule and get? The amounts of atoms of oxygen, because the molecule is made up of atoms, and so that's kind of leading us down the right path. So let's try that one out. 1 mole of hydrogen peroxide, and let's go to molecules of itself, and that's molecules of H2O2. Okay. Now, this is where we're kind of off-road. Remember I told you to add a little piece to your mole map yesterday with the ratio? So look at one hydrogen peroxide molecule. You're looking at it. What's inside?
2 hydrogens and 2 oxygens.
2 hydrogens and 2 oxygens. Nobody cares about hydrogens though, right? This is all about oxygen. So what do we now, like, give me the right terms that I'm working with here. For 1
mole
molecule of H2O2. Because remember, you're canceling. Mole was canceled. That's done. And now we're in molecules. Molecule will cancel. Oops. I mean, it's not done yet, but okay. Tell me what's on top. Two what? Atoms. Like, give me the right terms, right? 2 atoms of oxygen. Okay, so now we're just straight up oxygen. Yeah. So I want to go from atoms to mass. Can't quite do that, right? So what do I need to do from here? Go back to moles, but it's not normal moles, right? It's not moles of H2O2 we had. It's moles of what? Oxygen. So we're going to continue down here. What goes on bottom? Atoms, right? Atoms of oxygen go on bottom. And what goes on top? Say again? Moles of oxygen. What numbers go here? 1 on top and Avogadro's number. Whew. Okay, I've written this twice now, right? And now I'm in moles. So close. What do I need to do? Find the mass of oxygen from where?
Here at table.
What is it? 16. Where does that go?
On the top.
Because that's 16 grams of O for every 1 mole of O. Ta-da! 15.2. Is that right? Whatever my answer was earlier. No one wrote it down. 5 point. Okay, I got the numbers just in the correct places. 5.12. So here's the deal on this one. What did you see that was written twice? Avogadro's number, right? So I would not even try to calculate with Avogadro's number because that thing's going to cancel itself out, right? Because one's on top and one's on bottom. So don't even worry about that. This is now a really fast calculation. 0.16 times 2, 0.32, right? 0.32 times 16, about a third of 16 is about 5. Looks good. So you can even estimate to make sure that things make sense. That is a long process, but it should make sense to you in terms of going from moles to molecules, digging in the molecule, pulling out the atom, looking at the atom and go, okay, got to get to mass. So go back to our universal unit of mole, and then go to the mass of just the singular oxygens. There is another way to do it, but I'm going to hold off just because your brain is almost to capacity. Yeah. We're going to work with percents today, and so there is a method to do it with percents, but that's what we would apply after we learn percents, or we could apply. Somebody over here have a question? Okay, do me a favor, pull out a piece of paper. Call it percent composition of bubblegum. And then go to the Spitley address for me. Percent composition of bubblegum. And go to the Spitley address for me. Which now why you know you have a computer.
Can you go over one of the ratios?
Yeah. Like we just did on that hydroxide to oxygen one, like molecule to atom. That's what I just did. It's the same. It's like a ratio. It's an internal ratio. Yeah. All right. So when you look at this Bitly address, I would like for you to go ahead and read over it and see kind of what's going on, and then we'll get into the lab. I believe that is L. It is a lowercase l. So I'm going to give you guys about 3 minutes to look over that. Cody and Marmina's buddy, please grab a little absentee form. I've made some more copies. All right, go ahead on your paper and write down purpose, because you know that's kind of how we roll here. And then now look at somebody and command them with your eyes. Give them that weird wink. Okay. Okay, so at this point, we are going to be moving into partners, and then we're going to move to the lab. But both of your partners don't need laptops because you can read off of one, okay? So when I say go, one of your partners will have their laptop. You're going to come stand, or you can claim a spot in the lab, and then you can come stand by me in the middle lab station because I'm going to hand you a piece of sugar-free gum and a piece of double bubble with sugar in it. You're going to complete this lab. 2 notes of caution. We still have chemicals out, so I would just kind of push those to the side because we don't want to eat with chemicals nearby. And 2, 0, whenever you're massing out your gum, you put it on the scale, right? Would you want to put your gum right on the scale? What would be a good way to measure that, to weigh that without putting the gum on the scale? Or use the what? The wrapper. Thank you. The wrapper of the gum would be a great option. On the data table, it mentions wrappers mass. You don't have to mask the wrapper. You can zero out the wrapper, and then that would give you just to mask the gum. Okay? All right, and go. Come up here. You're fighting for it.
Okay.
Plug up your scale. Give me a second. I'll see if I need line up 2 by 2. Line up 2 by 2. Right here. And if you guys could clear the way.
Oh, yeah.
All right, remember we talked about the scale yesterday and I may have got a little irritated. Don't pick the scale up. Leave the scale down. Put the adapter in the back. Use your body. It moves. So you've got your purpose, you're getting your data started, and then you'll be chewing gum.
The wrapper's actually this one
All right, get those masses, and I need to see you shooting them. Chewing. Guys, you need to get started. Let's go. Is that exactly what I'm gonna ask for? All right, sugar-free. I'm just pointing at tables. You tell me your percent. Sugar-free.
49%.
Okay. Sugar-free.
5.6.
Okay. Back table.
52. 55.6.
Okay.
55.9.
If you guys would round, will you round up to an integer for me?
Okay,
Sorry, I'm thinking and writing. Back table. Okay.
51.
Anybody else?
50.
Another one here?
59.
59. I heard 57. 42. Any others? 54. 57. Okay, that looks good. All right, so that's our sugar-free. And then the sugar, which is the double bubble, just give me two over here. 26. Someone did the math wrong. I'm going to throw that out. Back table. Louder.
42.
42. 57. Keep going.
50.
50. I heard another 50. This area. Say again. 43. You guys know I'm deaf. So you got to be louder. Yeah. 44. Another.
52.
Another.
38.
Another.
55.
Another. Whoa. Also, I'm going to throw that one. Another. Ooh. Okay, so what I would anticipate for my three that I've circled here is that they didn't, well, no, you guys tell me this. First off, what we're noticing is what about the sugar-free gum? Supposedly has a higher percent composition of sugar, right? That's what we're looking at. And then the sugary gum has a lower percent composition of sugar. Let's talk about error. So error. So add this to your maybe your last question. Sources of error that could have occurred in the lab. You cannot list any like stupid human mistakes because we humans have control over how we could address these things. So anybody want to shout out an example of a source of error?
Calculation.
No, that would be a stupid human error that was avoidable.
Oh,
So slobber, yeah, saliva would be a more scientific word for that. So somebody, not all of us equally clean the slobber off. Okay, another back here. Yeah, CJ. Okay, so mechanism. So chewing mechanism. Ugh. So chewing mechanism, if you had a really good time with your gum, you chewed a lot, it might be a little different than if you just kind of leisurely talk to me while you're supposed to be chewing, things like that. Another over here. Hands up. I need one more. That's a stupid human error that can be avoided. Another? Well, the scale malfunction, like from vibrations in the room, could cause slight mass differences.
different types of gum.
But we have a comparison here, so that would be controlled for it because we've used both of them in all of our experiments. One more.
Like maybe if there was like food in your teeth. Like
Stuff in the gum. Oh, okay. That's a good one. Actually, I did not think of that. So what we're seeing is that we didn't control for every variable, but we did try to control for a lot of them. But these are some sources of error that could have contributed to our slight variations. But still, in the end, sugar-free gum still has a lot more difference, which gave us a higher mass percent of the sugar in the gum, right? So let's think. Was there sugar in the sugar-free gum? Yay or nay?
Yeah.
Why nay?
I think it's some kind of sugar substitute.
Okay, so they can't put sugar in the sugar-free gum because then we could sue them. Like,
Yes.
like nobody would be like, hold on, I'm gaining weight, I'm just chewing all this sugar-free gum. How am I getting more calories, right? So they say 0 or 5 calories or something like that in the sugar-free gum. So there must be something in there that still makes it taste sweet, but it's inside the gum and it's coming out in our saliva. So sugar is fairly water soluble. So all this sugar that was coming out of the sugar-y gum was water soluble, so therefore it was coming out in our saliva and we were tasting it. Has anybody ever heard of sugar alcohols? Sugar alcohols? Okay, that is what they put in gum to fake you out, to make you it taste sweet, but it's not actually sugar. It's not a carbohydrate. So it has an alcohol, which is an OH group on the end of it. So if that's on the end of this structure, I'm just going to call it R. If that's the case, is this group over here going to make this a polar or a non-polar compound? Kind of look at that. Is it equal or unequal? Unequal, so therefore this would be polar, right? So then we have a polar kind of molecule that's in place. Well, what's our saliva made of? Water, and water is polar. Therefore, polar dissolves polar. So our saliva is still sucking that sugar alcohol out, making it taste good, making it taste sweet, and we get a big difference. So they must put a lot of sugar alcohols in there. Who's ever heard the myth that, what was it, Orbit gum makes you fart? No one's ever heard this? Okay, sugar alcohols do some damage to your intestines, like not damage your intestines, but they make you fight flash and lengthy. They give you gas. So sugar alcohol can cause some social issues. Okay, so that is a lot of sugar alcohol. All of you guys see that sugar-free gum? Sorry. Okay, are you guys good with this? Who has finished these questions? Raise your hand. Who has finished? You have a minute left. Let's go. Finish these up. Sugar alcohols make you gassy. Yes. Now you know the trick. Have you finished this question?
Oh yeah, that's the sugar. 12 carbons, 22 hydrogen, carbon weights 12, yes. 12 times 144. What's the difference? 42 times 1 is 22. 11, oxygen.
If you don't remember anything else, I think you'll remember the gassy part of the story. How about you go get another one? Those little gray ones are all good. Finish where you are and then start writing down what's on the board for me, okay? This will be part of notes. We are going to keep working on that lab, but we're going to work on the other side. We're going to do another lab activity today. I'll call the lab activity. So finish that last question. If you need a legit calculator, so you're not using the computer for a calculator, please go grab one now. You got a really small number of moles. Yeah, that's okay. How much sugar? How much mass of sugar did you pull out of the gum? Like grams? 6 grams of sugar?
Oh. Like the actual.
How much sugar did you pull out of the gum?
1.09.
So 1 gram versus 342 grams, which is the mole of sugar, right? You're not going to have very much, so it makes sense for it to be small number. All right, and come back to me by halfway shutting your computer in 3, halfway shut your computer in 2, halfway shut your computer in 1. I need to, I can't compete with the internet. It's way cooler. Okay. And we're here together as a happy family, eyes up here. So halt on that lap for a moment. You know where this stuff is. It's on the website, okay? So I only want to do like 2 examples of percent composition. It's a very easy concept. Raise your hand if you've ever heard of percent. And it's just going to be part over whole, right? So if I wanted to figure out the percent of girls in this room, what would I do?
Girls divided by total number.
So total number of girls divided by
Total number.
total people
Times 100.
times 100. Every single time you do percent, it's based on 100, so you have to multiply by 100. So if you're finding the percent of a compound, you have to look for a singular element that you're interested in, and that would be told to you, like, for example, find the percent composition of magnesium in magnesium phosphate, okay? So the way you would approach that is very similar to our sugar and gum example. You would find the mass of that element in the compound, divided by the total compound mass, which is part over whole, and times by 100. All right, everybody write down magnesium phosphate. You have 10 seconds. Magnesium phosphate. I'm trying to get you to pull those polys out of your head. Guys, your computers are supposed to be halfway closed, so I know that I don't have to compete. Thank you. Audie, get me started. Magnesium phosphate. Okay, pause. Somebody pick up at your table. I hear O4. Okay, somebody else pick up. There's still some stuff that needs to be happening here. Say again. Who has a negative 2? This group's helping me out here, okay? Phosphate does not have a negative 2, it's got a negative. Okay, so where does that go? Okay, back table, keep helping me out here, come on. So that's the subscript on magnesium. I'm going to put parentheses around phosphate. I need a subscript down here. 2, right? So magnesium has a 2+ charge. Phosphate has a -3 charge. Crisscross both charges. You can't crisscross one. You always have to have both. So that's a pretty large compound. Here we go. I need mass of element, right? Everybody find magnesium in your periodic table. What's the mass?
24.31.
What is it? 24.31. So I have 3 magnesiums over a over 3 magnesiums plus, how many phosphori do I have? Phosphoruses.
2.
How many? 2, because this 2 distributes in to like that 1 that's next to P. 2 times 1 is 2. So this is a total 3 magnesium over 3 magnesium plus 2 phosphori plus, what else is left? 8 oxygen. So 2 times 4, right? 2 times 4 is 8. So this is our total on the bottom. And we're going to put masses in there, and we're going to solve. So we just kind of looked at the molecule and or the formula unit, and we dissected it for what it's worth. Now, everybody said magnesium's mass was what? 24.31. That's grams. So it's 3 times the mass of magnesium. And now we're going to add up the rest of these. So 3 times 24.31. Allison's table, what's phosphorus weigh? So that times 2, right? You don't have to tell me the number yet, okay? 30.97, is that what you said? Okay. So that's 2 magnesium, 3 magnesium plus 2 phosphoruses plus 8 times what for oxygen, everybody? 16. All right, now one would not have to write out this entirely. I'm just like putting this on the board so you can see the thought process behind this. So magnesium over total times 100. What do we get for percent magnesium? Calculate. If you don't have a calculator, go grab one because I know you're not doing this in your head. Go. And muscle memory kicks in when you freak out on a test and you're like, oh no, how am I calculating? So maybe confer at your table the molar mass total before you get too far in. Colin, you want a calculator, sir?
Too fast for me.
Thank you.
You guys get 27 points.
Alright guys, so what do we get for the molar mass the total mass of the magnesia here?
72.9.
72.98? 70, okay, depends on how accurate your field table is. 72 point what? 93 grams, okay. What's the total for all of this? 262.87. Okay, 72.93 divided by 262.87 times 100 is what?
27.7.
How much?
27.7.
20? That sounds better. 20 what?
7.7.
27.7%. Okay. So that's percent magnesium. All right, so I want you guys to do that same thing, same process for phosphorus. For phosphorus P and for oxygen. Can I get a confirmation on this? How many people got this? Majority rules, yeah.
So like, I rounded it up to like 28%.
You're fine to round it up. We're not given any indication here of sig figs whatsoever. I would generally probably call that 28%, but you're okay. I just wanted to keep it a little bit more specific. Do the same process for phosphorus and oxygen. Now, go. Phosphorus and oxygen. We've already done the hard part of calculating, so this will be easy. I'll burn all over. All right, can I get a phosphorus? Up here, phosphorus.
3.95.
Say again? 23.5? Okay, I'm just going to go with that because I got a couple people say yeah. All right, so how can I make my last one really easy?
Subtract it from 100.
Why are we looking at 100? Why is it an important part of this? Because all percents always what? Always up to 100. So I've got magnesium, phosphorus, and oxygen, and they have to total to 100. So versus doing this process again, I'm just going to say, hey, 100 is the total percent. Subtract the 23.5% phosphorus. Subtract the 20, what was it for magnesium? 27.7% for magnesium. And that's going to give me my percent oxygen, which is what, guys? 48.8 sounds good. Give me a thumbs up if you feel okay with percents as it applies in chemistry, not just the real world. Okay, so thank you. You can put your hands down. So now we're going to take this percent composition, which means like the analytical way of looking at a composition and saying, well, how much of this and how much of this and how much of this do I have? We're going to take this and apply it to a system where we have a value for a compound, and we want to figure out how much of that compound is made of, you know, one of these elements here. So we have 54 grams of compound, magnesium phosphate. I want to know how many grams of that's oxygen. Go. See if you guys can figure it out. Think like in math class how you approach this. Don't make this hard. Yeah, because this is magnesium phosphate. We already found all the percents that it requires. Augie, get me started. Looks like you're done. I'm hoping you took the easy way on this one. Can you help me out?
26.
Don't give me the answer. I don't. That doesn't help me. Give me like the process. Teach a fish.
Multiply the percentage by the grams.
Okay, so you're looking at total sample, right? Only a part of that total sample is oxygen. what's the part that's made up of oxygen? What percentage?
Three.
Right, so we just got this here. So we know that about half of all samples of magnesium sulfate, about half of it's going to be oxygen, right? So I can actually just do a little guesstimation first. If I got a 54-gram sample, approximately how much should be oxygen? 25, 26, someplace around there, because that's about 50% of 54. So then how would I mathematically show that? I need to go 54 grams total, and then multiply that by this percent. But if I multiply by 48.8, that's going to be a huge number, right? So, Audie, what did you do?
Divide that.
Right, so you're going to divide by 100, which backs our decimal up twice. Boom, boom. So we're taking the percent as a decimal, and we multiply. That's why I said think about this in math class. Who did this in, like, 7th grade math? 5th grade, I'm not sure. 3rd grade, I have no idea. But you've done things like this in math before. It's the same application. And what was it, 20 what?
26, 23.
Point what? 3, 5, thanks, grams. How many sig figs should be here?
2.
2, so let's call that 26 grams of oxygen. And you could do that for magnesium or for phosphorus, but I specifically wanted to test for oxygen. And that's it. That's all we're doing with percents. We're going to practice this again, though. Go to my website. I will pull this up here for you as well so you can see where we are. So just go to my website. I'll have you go like to the actual place I'm going in just a second. Because I have this here, this will make it easier for you. So I've provided you with a simulation to help you see how this would be applied in a lab, but we need to look at this one more time on a practice kind of scale. I want you guys to do 1 and 2, and then we'll talk about those, and then we'll do 3 together. Okay? Go. It's very similar to what we were just doing. Yeah, please, you can do it. Actually, no, I'm sorry. Do this on your bubblegum lab sheet, because whenever you turn this in, I can get both of those at the same time. So call this a simulation. Call it a simulation. And then complete 1 and 2 on your bubblegum sheet. So show your work for me so that I'm not just getting calculator answers because, you know, it's kind of fun. All right, Michaela's table. What's silver weigh? What is one silver weigh for me? 107.87 grams. Good. Bennett, what's your table? Can you guys tell me the whole silver sulfide's mass?
It was I didn't know separately.
So it is two something.
250.74.
250. Is that right?
250.
No.
Because I did mine separately.
Okay, but so take that times 2. Add what's sulfur weigh, guys? 32.07. What's this total? 247. Point what?
81.
Something like that. Okay. And times 100. Everybody, what's your percent? 87. I'm just going to go 87% because, again, we don't have any indication of sig figs, so let's just kind of round that to an integer. All right, Brennett's table. How would I find the, 10 grams of a 10-gram sample? 10-gram sample of silver sulfide. How much of that is silver? How would I approach that? So this percent is silver, right? So how do I write the percent down now? 0.87 times what? 10 grams, which we can do that in our head. Which is what, guys? 8.7. So we know that makes sense because if a whole 10-gram sample is present, I can't have more than 10 grams. I have to have less. It's about 90%. That makes sense. It's about 9 grams. Okay, part 3. When we get to simulation day, I'll save that. No rush. I want you guys to think on 3 for a second about the terminology. Write this down. We'll try to do B and C together if I can. Feel free to talk it out.
Thank you.
If you need a quick second to Google hydrate, that's fine. But I do think you know what it is. Just think about it. In chemistry, though, chemistry complex. All right, I got you. If you know hydrate means you have been hydrated, you have water in you as a person, it kind of makes sense for in chemistry we mention hydrates to be crystalline structures, like an ionic crystalline structure, but it has water embedded in it, in the crystal, and therefore we actually have a symbol for that. Like down here, you've seen this hydrate before, or one similar to it. So crystals with water embedded, hydrate. Crystals without water embedded, anhydrate. Because an means what? Not, or without, or not, opposite, okay? So now if we're going to find the mass of water, notice it's not just a single element now, it's like the whole water aspect of this compound. We're going to find the percent mass of water of, say this for me, barium hydroxide, octahydrate. What does this dot right here mean?
It's just a dot.
It's just a dot, right? It's not multiplication. Do not multiply masses. Keep it as summation. Okay, so I need to find the percent mass of water. Okay, so percent mass of water and barium hydroxide octahydrate. How many waters are in here? 8. So that's going to be 8 times the mass of water, because that's the part we're concerned about. Then we're going to divide it by what? Everything, right? The whole mass of barium hydroxide octahydrate. All right, so 8 times what's the mass of water? Give me an approximation here. 18.02. We can add that up, right? 2 hydrogens at 1.008 each, plus an oxygen at 16. And then you guys are going to have to do that. Go. Get your mass of barium hydroxide. Octahydrate.
Oh wait, no, you did not. That's not right. Did you get? Oh, okay.
I need to see hands on the calculator. I want to see you adding this up, because it's not just, it takes a minute to kind of organize this up. It's not just adding. All right, I need a molar mass for barium hydroxide octahydrate. Raise your hand if you think you got this right. Raise your hand for barium hydroxide octahydrate's molar mass. I have 4 people confident in there, 5 people confident in calculation skills. It starts with a what?
3.
A 3. Okay, raise your hand if you think you're right. Okay, this is literally adding up. A barium, which weighs what? 137.32 plus 2 oxygens that weigh what? 16 total. Sorry, I mean 16 times 2. And then 2 hydrogens that weigh what? 1.01 each. So that's 2 of those. And then you're adding 8 waters. 8 waters weigh 8 times 18.02. So make sure you're that is a simple kind of addition. You just have to process how many of each one of those you have. That is 315.51 grams total. Times that by 100, and what do we get for percent?
45.46.
I hear 40s.
45.
45.69%. Yes. 45.69% water. All right, go ahead and put your laptops up. We'll complete this on Monday. We're not quite done yet. We actually have the actual simulation part of this. It is 2:14. If you could shut down, that would be amazing. Shut down so these things can rest over the weekend. Doing one